Welcome to lecture 26, entirely devoted to the L'Hopital theorem. This theorem deals with limits of the form x goes to x naught of f of x divided by g of x, where x naught is in the extended real line, so can be finite or infinite. Now, this theorem offers an additional tool for solving limit of this type, and it makes use of derivatives. So this is why we are discussing this theorem after the lecture on derivatives. Now, the condition of applicability of the theorem are the following. First condition, we have a limit as x goes to x naught of f of x divided by g of x, which is one of the undeterminate forms 0 over 0 or plus or minus infinity divided by plus or minus infinity, right? Where, again, x naught is in the extended real line. Second, we have that f and g are defined around x naught. Okay, so the two functions are defined in a neighborhood of the point x naught. Can it be finite or infinite, where we are taking the limit? The same thing is required for f prime and g prime. And finally, we also require that g and g prime are different from 0 around x naught. Third condition is that the limits as x goes to x naught of f prime of x divided by g prime of x exists. So if we have all these three conditions, so let's review it quickly. So if we have an undeterminate form of the type 0 over 0 or infinity over infinity, then we know that these two functions, f and g, together with their derivatives, are defined around x naught, and also we know that g and g prime are different from 0 in that neighborhood of x naught, and we finally see that the limit of the ratio of the derivatives exists. Then we can conclude, then we can say that the limit as x goes to x naught of f of x divided by g of x is equal to the limit as x goes to x naught of f prime of x divided by g prime of x. In other words, rather than trying to solve the limit of f of x divided by g of x, we'll solve the limit of f prime divided g prime. An important note is the following. It can happen that after one application, so if after one application of the theorem, the new limit satisfies the three hypotheses 1, 2, and 3, then we can reapply the theorem. Let me show immediately one example of application of the theorem. Let's consider the limit as x goes to plus infinity of 2 cosine of 3x plus x divided by x. Now, we immediately realize that this limit is one of the undeterminate forms covered by the L'Hopital theorem, because we have infinity at the denominator and infinity at the numerator, right? Now, we might think, okay, let's see if we can apply the L'Hopital theorem and say that this is just equal to the limit as x goes to plus infinity of the ratio of the derivatives. Now, if we take the derivatives of the numerator, we get 2 times, well, the derivative of the cosine is minus sine of 3x, and then of course we need to multiply by 3 again, plus 1 divided by 1, right? So this is the limit as x goes to plus infinity of 1 minus 6 times sine of 3x. And well, this limit does not exist, right? So does not exist, because we immediately see that we have the sine of 3x, which we have already proved has no limit. If we want to prove this more formally, we need to identify basically 2 sequences with different limits. Let me call the first sequence an. Let's say, for example, that we want to make the sine to be equal to 1, okay? And remember that, I mean, if we want to make the sine equal to 1, we know that this happens at pi over 2 plus 2 pi n. So we can say that if we take an to be equal to 1/3 of pi half plus 2 pi n, we have that the limit becomes 1 minus 6, because clearly sine of 3x is now 1, so this clearly is something that goes to minus 5, so we have a limit minus 5. And if instead we want to make the limit, we take another sequence bn and we want to make this limit to be minus 1, okay, so we know that this happens at minus pi over 2 minus 2 pi n, for example, or if you like, minus pi over 2 plus 2 pi n. So what we get is that bn is again 1 over 3, but with the minus in front, and we put pi over 2 plus 2 pi n. Well, in this case the limit becomes 1 plus 6, which goes to 7. So this proves that because 5 is different from 7, clearly this limit does not exist. So can we conclude then that the initial limit has no limit? It would be wrong, okay? Wrong conclusion. 2 cosine of 3x plus x divided by x has no limit. So that would be the wrong conclusion. In fact, one of the conditions of applicability of the limit was that the third one was saying that to conclude that the two limits, the ratio of f of x and g of x and the ratio of f prime of x and g prime of x, they have the same limit, is that the second one has a limit. We are now, however, in a situation where the second limit, the limit of the ratio of derivatives, has no limit. So we cannot conclude anything about the first limit. Well, in fact, by just doing a simple application of the policeman theorem, what can we say? Well, we have a fraction 2 cosine of 3x plus x divided by x, right? So if we write the inequality, we need to have something to the right which is larger. So we keep the same denominator, but we'll replace cosine of 3x with just 1. Okay, so we get 2 plus x on the right, and on the left we will replace with something smaller. So we will replace cosine of 3x with minus 1, so we have minus 2 plus x. But we clearly see that when x goes to plus infinity, this will go to 1, this will go to 1, and then by the policeman theorem we see that this function indeed has a limit to 1. So this proves that we were not in the condition to apply the L'Hopital theorem. Okay, let's now pass to a very important example. This will clarify a number of things that we already mentioned in the previous lectures. So important example. Let's consider this limit. Limit as x goes to 0 of e to the x minus 1 minus sine of x plus x squared, all divided by sine square of x. Let's immediately check that this is one undeterminate form. Well, as x goes to 0, the denominator goes to 0, and also the numerator, because we have e to the 0 minus 1 is 0, sine of x is 0, so yes, this is clearly 0 over 0. Okay? Now, let's try to solve this. Let's first try to use the fundamental limits. So, first approach. Now, we immediately recognize some terms of the fundamental limits. So, one way of approaching the problem might be this one. So, we see that we have e to the x minus 1 divided by x times x, so that we, in the numerator, we already have something that we know. Then we might divide and multiply by x, sine of x, and again we have something that we know, and we leave x to the square. At the denominator instead, we might divide and multiply by x squared, right? Okay, good. We see that we can simplify 1x, so this becomes limit as x goes to 0 of e to the x minus 1 divided by x minus sine of x divided by x plus x, and then we have sine of x divided by x, all this to the square times x. And now we know that this tends to 1, this tends to 1, this tends to 1. So we didn't fix the problem because we are still in a situation where we have 0 over 0. So this first approach doesn't seem to work. Okay, let's now try to apply the asymptotic equivalence. Now, what can we say? Well, for example, we know that e to the x minus 1 is asymptotically equivalent to x when x goes to 0, right? And also sine of x is asymptotically equivalent to x. And then we can say that sine square of x is asymptotically equivalent to x squared. Okay, so this would give us what? Let's see. We will have x minus x plus x squared divided by x squared. So we simplify this, and we might conclude that this limit is 1. Okay, so this might seem a first result. But let's see now what happens if we apply the L'Hopital theorem to the same limit, because we are in the condition of applicability. We have one of the undetermined forms where we can apply the L'Hopital theorem, 0 over 0. So let's go to the third approach. And let's see if this gives a result which is consistent with the previous one. So we have limit as x goes to 0 of e to the x minus 1 minus sine of x plus x to the square divided by sine square of x. Now let's apply L'Hopital. Let me just write this, okay, to say that we have a first application of the L'Hopital theorem. This gives the limit as x goes to 0. We need to take the derivative, right? So we have e to the x, derivative of minus 1 is 0. Derivative of minus sine of x is minus cosine of x plus 2x. And then we have 2 sine of x cosine of x. Now let's notice that we still have an undetermined form here. Why is that? Because for x that goes to 0, e to the x becomes 1, just like cosine of x. So on top we have 0, and also the denominator we have 0. But we are still in the condition then of applicability of the L'Hopital theorem, so we go for another application. So if we take another derivative, what we get? Well, e to the x. Now we have now plus sine of x plus 2. At the denominator instead we have 2, okay, this is just a constant, and then we have the derivative of a product. If we take the first derivative of sine of x, we have cosine of x times cosine of x, which is cosine square of x, and then we need to take the derivative of the cosine, which is minus sine of x, so minus sine square of x. Good. And are we still in an undetermined form? Well, not really now, because we can now just replace x equals 0. This is a continuous function, and we have at this point 3 divided by simply 2. Well, so this is a different result from what we got in the second approach. But this is the correct one, and this is the wrong one. Okay? This is the wrong one because it is always a bad idea to use asymptotic equivalence when doing limits. So let's try to revisit the second approach. Okay, second approach revisited. So the right approach is not to use the asymptotic equivalence, but to use the infinitesimal. So we might write e to the x minus 1 is equal to x plus little o of x, and then sine of x is equal to x plus little o of x, and then we have x to the square. Well, we can consider this to be little o of x once again, and then we have that the sine square of x is equal to x to the square plus little o of x. Okay, let's see what happens now if we replace this in the original fraction. So we have x plus little o of x that replaces e to the x minus 1. Then we have minus x plus little o of x that replace sine of x, and another little o of x that replaces x to the square, and a denominator we have x to the square plus little o of x. But this is nothing else that x and minus x, they just can be simplified, so we get little o of x at the numerator divided by x to the square plus little o of x, which is something that we can divide and multiply the numerator by x, so we get x times little o of x divided by x, and then we can factor out at the denominator x to the square, so that we have 1 plus little o of, sorry, this is x square o of x to the square divided by x to the square. And now we see that as x goes to 0, this will go to 0, this will go to 0. So once again we are back into the undeterminate form 0 over 0. So this tells us that applying the infinitesimal to solve the limit doesn't work. Now, and this is an important consideration that we need to do. Okay, important observation. If L'Hopital requires 2 iterations, the limit cannot be solved by the short expansion. So let me comment a little bit more on this. Let's review what we have done so far. Okay, so we started with this limit. We were given this limit. We realized that we were in the undetermined form 0 over 0. First approach was just applying the fundamental limits, but the first approach didn't help because we were still in the undetermined form. Okay, so second approach, we try to solve the limit by using the asymptotic equivalence, and we got a result of 1. Okay, then we went on for the De L'Hopital theorem, and we found a different limit, 3 over 2. So which one is the correct one? Well, we might think that the use of the asymptotic equivalence was not correct. So we revisited the second approach by just using the short expansion, but still we were in the undetermined form. So the final conclusion is that when using the De L'Hopital theorem, basically we had to apply the theorem twice, because after the first application we were still in the undetermined form 0 over 0. So we had to do this again. Now when this happens, it means that the short expansion is not enough. Indeed, we will find out in one of the next lectures that the proper expansion would need more than just one term. So the short expansion usually is taking the first term of the possible expansion of a function, which is not enough. And this is clearly showed by this double application of the L'Hopital theorem. And this is exactly where we are now. So the important observation that we did is this: if the L'Hopital requires two iterations, and we know that the L'Hopital is correct at that point and gives the limit 3 over 2, so that implies that we are in a situation where the limit cannot be solved by just a short expansion. Now, another general observation regarding the applicability of the L'Hopital theorem is that has a limited utility. Okay, so limited utility, I would say 5% of the limit, due to the fact that functions get worse by derivation. So what I'm saying is that if we start with a function with the ratio f of x divided by g of x for some x that goes to x naught, and we want to try to get a better limit by taking the limit as x goes to x naught of f prime of x divided by g prime of x, well, this usually tends to be worse, just because every function gets more complex after applying the derivative. So only 5%, roughly in 5% of the cases, you get some really advantage in doing this, okay, in taking the derivative. Let's review together some example where this actually works. Example. Let's consider the limit as x goes to plus infinity of x times pi over 2 minus the arc tangent of x. Now, this limit is of the form infinity times what? Well, we have pi over 2 minus arc tangent of plus infinity, so this is 0. Clearly this is an undetermined form, but is not still in the form that we need to apply the De L'Hopital theorem, so we might need to make this transformation limit as x goes to plus infinity of pi over 2 minus arc tangent of x, so that we still have a 0 on top. But now that x that multiplies at the numerator becomes 1 over x at the denominator, and this is now 0 over 0. So we are now in the situation where we can apply the L'Hopital theorem. Let me write here L'Hopital. And what we get now is limit as x goes to plus infinity well, we need to take the derivative of the numerator, which is minus 1 over 1 plus x to the square, and we get minus 1 over x to the square. And this is just like the limit as x goes to plus infinity. By simplifying everything, we get just x to the square divided by 1 plus x to the square, which is clearly equal to 1. Okay, so this is where we really got an advantage by taking the derivative. Now, an alternative approach would have been the following: just rewriting pi over 2 minus arc tangent of x. If you remember, we introduced in one of the first lectures this identity. We know that this is equal to arc tangent of 1 over x, okay? And if we use this, well, the limit becomes limit as x goes to plus infinity of, instead of writing having this pi over 2 minus arctangent of x, we'll just replace this with arctangent of 1 over x, so that we get arctangent of 1 over x at the numerator divided by 1 over x. Well, but this clearly, by the change of variable y equal to 1 over x, this is clearly fundamental limits, and we know that this is 1, so we clearly get the same result. Another interesting example is the following. Let's consider this limit. Limit of this fraction, arc cosine of x minus pi divided by the square root of 1 plus x, where x goes to minus 1 plus. And we need to have this to have the denominator properly defined, right? Because 1 plus x has to be a positive number, so x can tend to minus 1 from the right, from basically taking values which sits to the right of minus 1, so that 1 plus x is always positive. And we immediately recognize this to be another undetermined form, because when x goes to minus 1, our cosine goes to pi. I will be now plotting as a reminder the arc cosine function. Okay, if we have x, so the arc cosine function, something like this, where this is plus 1, this is minus 1, this is 0, this is pi over 2, and this is pi. Okay, so this is the arc cosine function. And we see that when x tends to minus 1 from its right to minus 1 plus, we are clearly in this part of the graph, okay? So our cosine is below pi, and of course it will get closer and closer to pi as x goes to minus 1. So we have 0 at the numerator, and of course we have 0 at the denominator, because the square root of 1 plus x tends to 0 when x goes to minus 1. We are again in one of the situations where we can apply the L'Hopital theorem, so we can rewrite x that goes to minus 1 plus, and now we take the derivative of both numerator and denominator. Now what do we get? We get minus 1 divided by square root of 1 minus x to the square, and then we have 1 divided by 2 square root of 1 plus x And this can also be re-expressed as limit as x. Oh, I will use this on the right. Okay, so I will write limit as x goes to -1 plus, and these two goes at the numerator. We can rewrite this as square root of 1 plus x divided by, now we can rewrite the square root of 1 minus x squared as the product of 1 plus x times 1 minus x, right? So we can easily simplify these two, and now we can simply recognize a continuous function that with the replacement x equal to -1 gives minus square root of 2. Okay, so this is a nice result which we can use to write some kind of approximation of the function arc cosine of x, because now let me restate the result that we have. We had that the arc cosine of x minus pi divided by the square root of 1 plus x tends to -2 for x that goes to -1 to its right. But this is just like saying that the arc cosine of x minus pi, right, is basically equal to minus square root of 2 times square root of 1 plus x plus a little o of square root of 1 plus x. We can say that, okay, so because these the left hand side and the right hand side, so this part, let's say this term and this term, they just differ of a quantity which goes to 0 when x goes to -1, so when the square root of 1 plus x goes to 0, right? So also we can re-express this in as arc cosine of x equal to pi minus square root of 2 times square root of 1 plus x plus little o of square root of 1 plus x. And of course I'm always assuming that x goes to -1 plus. All right, and an even more meaningful expression can be obtained by setting y equal to 1 plus x, because of course when x goes to -1 plus, we have that y goes to 0 plus, right? So we can rewrite this as the arc cosine of y minus 1, which is equal to pi minus square root of 2 of square root of y plus little o of square root of y for y that goes to 0 plus. Let's try to interpret this result. What we are saying is that remember that we started from the arc cosine function. So we said that we had the arc cosine function, which is something like this. This is 1, this is -1. We know that this is pi over 2. We know that this is pi, and we were approaching -1 from its right. Okay, so we said that basically this approximation which is this one. Okay, this approximation is valid when x tends to -1 plus. So we can replace the arc cosine function with a function pi minus square root of 1 plus x, which we can imagine would be a function like this. Okay, so we can say that this function is pi minus square root of 1 plus x. Okay, so this approximation is valid when we get close to -1 from its right, and this might be useful in some future developments. And this also makes sense because if we remind ourselves what is the shape of the square root of y, let's say that this is y, and clearly remember that this is square root of y. Okay, so if we take the opposite, right, so this would be minus square root of y, and if we now shift this by pi upward, what we get is a function like this. So this would be pi minus square root of y, which is something similar to what we have drawn here, right? So this, basically this part of the graph is pretty much the same shape of this, so this makes sense of this approximation.